So let's make sense of the notes. We call that flipping Hess's law. So when we look at example one, we notice we have two reactions listed and they combine to make the overall reaction down there. So carbon plus oxygen gas gives us CO2. So that overall reaction takes place in two steps. So in the first step, we have carbon and we have 1/2 of the oxygen gas, right? So two bonded oxygens. We're just taking one of those oxygens and combining with the carbon. That's all that means. And we're making CO. In the second step, this carbon monoxide there joins up with the other oxygen from our O2 pair and makes CO2. So we see it happening in two steps. The reason we split it up is because of the energy involved. So we can see that in the first step, it's exothermic because we're losing energy in the process. And it takes that much energy for the carbon to bond with 1/2 of the oxygens. And in the second step, we're losing more energy, for the CO to bond with the other oxygen. And so those are the energies involved. We want to figure out what the overall energy involved is with this. So we just go through and we start canceling things out. So there's a carbon here, there's a carbon there. So we've accounted for that carbon. Nothing really changed there. Here we have 1/2 of the oxygen, 1/2. So 1/2 plus 1/2 gives us one full oxygen. We've accounted for that there. We see that we have CO2 as a product. CO2 is a product there. So what about the carbon monoxide in there? Since that's an intermediate, we're just forming it and we're using it, that cancels out. So it tells us in order for us to get to this overall reaction, we really didn't have to manipulate anything. That previous slide showed us all the available manipulations that we could do. In this case, we didn't have to manipulate anything. So this enthalpy and this enthalpy, the two delta H's will just add up to whatever enthalpy is there. And so when I plug that in my calculation, negative 110.5 plus negative 283.0, accounting for significant figures, gives me negative 393.5. So the total enthalpy for this reaction to be negative 393.5 degrees.